Hi there! In this video I want to show how to build another useful device for your home lab. It's a current transformer adapter for your multimeter or scope. With that you can measure AC currents up to 100 amps very easily. It opens up to allow it to fit around wires without the need for breaking the circuit. The device is based on a very popular and easily obtainable SCT013-100 costing around 5 to 6 pounds. It's used a lot with Arduinos and in the open energy monitoring system. In my case, I've already made my own energy monitor a while ago using the P-Sphere PZEM-022 module, which has its own current transformer. I add a link to the two videos building this if you have not seen it. It can monitor energy, but I'm using it as a power meter, as a convenient way to measure power factor, real and apparent power of all kinds of mains power devices. And of course, you may already have a clamp multimeter, which does allow you to measure currents without needing to break the circuit, like for a normal multimeter in current mode. This Unity UT210E, for example, uses a clamp with Hall effect sensors to measure AC and DC currents. A normal multimeter usually has many ranges to allow precise DC and AC current measurements, like for example this Bryman BM235 measuring an AC current. But there are some multimeters that lack current measurement, for example the popular Fluke 101. And of course an oscilloscope without any special probes will only measure voltages. So you may ask, if some or all of these devices are available, what's the point of getting an extra current transformer? To begin with, they all excel at some stuff and are not so great at others. The multimeter, for example, can measure a wide range of voltages and currents at very high precision, but it's limited to 10 amps max, and even that only for a very short duration. The clamp meter has a much wider range for current, but with much less accuracy than the multimeter. The power meter is limited to AC mains, but in contrast to the other devices, it can measure voltage, current and phase angle simultaneously to calculate power and power factor and energy consumption. And of course the scope allows you to see the waveform, but only measures volts. Adding a current transformer expands the capability of each of these devices. It changes a simple multimeter to a clamp multimeter, allowing it to measure AC currents of up to 100 amps for an unlimited time without breaking the circuit. In case of the UT210E clamp meter, it actually improves the accuracy for AC current measurements, and for the scope, it finally lets it measure AC currents directly. I covered current transformers back when building the power meter, but as a brief recap, it's a ring-shaped core with a coil, which is a secondary. The primary is the single wire for which you want to measure the current, and which goes right through the core. If the to-be measured current is I input, the current transformer produces an output current I out that depends on the ratio of the primary and secondary windings. In our case of the SCT013-100, these values are 1 and 2000, so the transformer effectively divides the current by 2000. What that means is shown in the little table here. The top row shows some example input currents and the bottom row the output currents the transformer will produce. A ratio of 1 to 2000 means you need to do some mental doubling, so measuring 5 milliamps on the transformer output, for example, means 10 amp is flowing. If that seems too troublesome, you can loop the to-be measured wire so it goes twice through the core. The primary winding is now 2, which means in accordance with the formula, the ratio is now 1 to 1000, and 10 amps in the primary causes a current of 10 milliamps in the secondary. Very straightforward and easy. But of course, the maximum current you can measure with this transformer is now halved from 100 amps down to 50 amps. It is very important that the current transformer is never used without a load connected to the secondary coil, because that can produce dangerously high voltages that can shock you and damage the transformer. In a sense, a current transformer is the complete opposite of a normal voltage transformer. A voltage transformer is quite happy when no load is connected to its secondary winding, but if you shorten it, the high current flow will cause it to overheat and eventually burn. On a current transformer, normal operation is when the secondary is shortened, or very nearly so, while it's in danger of destroying itself through arcing if no load is connected. While nearly everyone is well aware that shortening a voltage transformer is a bad thing, not many know that not loading a current transformer is equally bad. I guess that's the reason that the makers of the SCT013-100 decided to add this bidirectional transient voltage suppression diode into the housing. It basically shortens the secondary before the voltage spikes get to a dangerous level. And while we're at the datasheet, I want to point out a few things. The rated input is 100 amps, which produces 50 milliamps based on the ratio of 1 to 2000. The accuracy is actually quite good, with ±1%, which beats the Uni-T, for example. It states the max sampling resistor is 10 ohms, more about that later. Last not least, take a note that the AC frequency range is from 50 Hz to 1 kHz, and the electrical safety parameters means it's good for use in main circuits, even three-phase applications. Getting a current out of a current transformer is only convenient for use with multimeters that have 50 milliamps or so AC current range. To be able to use it with my scope or other multimeters, it's much more useful to add a sampling resistor so that we convert the current directly into a voltage drop across the resistor. Because of the transient voltage suppression diode, we can even safely add a little switch to select a different sampling resistor. The manufacturer datasheet includes this table showing the effects of different sampling resistor values. It is a bit strange since earlier in the datasheet they stated the maximum sampling resistor as 10 ohms, but this diagram just starts at 10 ohms and goes up to 500 ohms. Anyway, we can clearly see that at higher resistance values the voltage gets into the range of the TVS, which seems to be a 5 point something volt type, judging from the way the curve flattens just above 5 volts. That makes sense because, as I mentioned, lots of these are connected to AD converters in various energy monitoring circuits. So what are good values for the sampling resistor? I consider 2, 20 and 200 ohms. The reason for these values is that they produce easy relationships between amps and volts, as you can see in the table. After doing some tests, I decided to discount the 2 ohm resistor because even good multimeters are not that great in measuring tiny AC millivolt accurately. Many AC accuracy specs are only valid if the AC voltage is at least some % of full scale value. So 20 ohms is a good value that with 1 volt at 100 amps still stays well clear of the TVS clamping. To measure really low currents better, I decided to make the other choice a 200 ohm resistor, which gives 10 times better resolution for low currents. This range will be affected by the TVS, but only at currents well above 10 amps, and if it comes to that, we can simply switch back to the 20 ohm value. In line with scope probes, I will name the two modes times 10 and times 100 for the multiplier needed to convert the output in volts to the equivalent current in amps. Finally, if you know you will be measuring really small currents, nothing stops you from looping the measured wire 10 times through the core, and now you have gained another 10 times better resolution at the cost of reducing the max allowed current to 1/10 of what it was with a single pass through the core. One last note on the design. The drawback of the circuit on the left is that during the moment of switching between the two resistors, there is no load across the current transformer. In case of the SCT013-100, that's fine because the TVS will limit the spike to about 5 volts, which a scope or multimeter will tolerate briefly even if in the millivolt range. At least it won't damage it. If you use another current transformer, that may or may not have a built-in TVS, so you should definitely go for the alternative circuit on the right. As you can see in this circuit, there is always a 200 ohm load across the current transformer. All the switch does is to add another resistor in parallel so that the resulting total value drops from 200 to 20 ohms. That additional resistor needs to be theoretically 22.222 and so on ohms, which of course is impossible to get. Depending on what accuracy you want to achieve, you could try a 22.1 ohm resistor, but my suggestion is to get a 40 and a 50 ohm resistor and put them in parallel. Those values are available, but still rather expensive as 1% or even 0.1% tolerance, and you probably want to use at least 1% tolerant resistor. Uncommon values like 50 ohms are available for a price, but 100 ohms is much easier to get at good tolerances. Often you can get 20 or more 100 ohm resistors for the price of a single 50 ohm with the same tolerance. So substitution is important to make this affordable. The drawback is that it's more effort to wire it all up, but on the plus side you will have some precision 100 ohm resistors left over, which is always useful to have. Same principle for the 40 ohms. You may find good 20 ohm resistors, but it's more likely you will need to get 4 times 10 ohms in series instead. As a last resort, you could use a 20-turn trimmer and calibrate the correct value of 22.222 by either measuring the resistance directly or measuring the voltage when a known current is measured with the transformer. In either case, the accuracy of your current transformer then depends on the accuracy of your calibration. But enough of the theory, let's build it. I decided to keep the current transformer and its 3.5mm TRS plug as it is and put a matching socket into a little box that houses the switch, the resistors and a BNC socket. As we are talking AC millivolts here, it's a good idea to use a metal housing for shielding. A main user of this box will be my scope, so a BNC connector is convenient for that. Using what I had as leftover precision resistors, I went with a simple circuit that needs the TVS to be safe. You see 4 resistors because I only had 10 and 100 ohm 0.1% resistors. Switch and sockets are installed, and all that's needed is wiring it up. The box is just big enough to do the soldering. The red wire is the signal, ground is a blank wire, which is a bit tricky to see. Of course, the box itself is also on ground potential through the 2 sockets. The common ground point is the BNC connector. It's definitely not my most beautiful soldering, but hey, it works. Let's cover it and never look at it again. A simple way to test the wiring for correctness is to check the resistance on the output with no current transformer connected. It should be 200 ohms or 20 ohms depending on the switch. The small deviation is due to not using rel mode to null the leads before measuring. I'm comparing the converted output of the current transformer measured with the blue multimeter against the current flowing through the big resistor on the heatsink, the core of the current transformer, and the red multimeter. With a slightly fluctuating 770 milliamps of current flowing through the transformer, the times 100 setting produces 7.75 millivolts and 77 millivolts in the times 10 setting. That's pretty good, especially at this low current, considering this is capable of going up to 100 amps. Giving it a bit more input current, around 2.4 amps now, and we can see that both the times 100 and times 10 setting are close. You can also see the problem in using mains AC as source, as voltage and therefore the current continuously fluctuates, so it's very hard to compare values for accuracy. 3.7 amps now, and everything is working as expected. And speaking of measuring mains, with a current transformer or clamp meter available, you should make yourself an extension cable like this, where you can clamp each wire separately. Here I am using it to clamp the live wire and measure the current of a fan heater in times 10 mode. First, only the fan motor is running and we can see about 200 milliamps. With the first heating element on, that jumps to 4.3 amps and then to 8.2 amps with the second one on in addition. In times 100 mode, we lose a digit in accuracy. That's why the times 10 mode is so useful for smaller currents, and yes, even 8 amps is considered small in this context. Just for fun, let's see how much current is flowing in this soldering iron tip, which I temporarily replaced with a piece of wire. Wow, 38 amps, that is close to the limit of the times 10 mode. But the times 100 mode says the same, so 38 amps is still fine to measure in times 10 mode. The next test for using the current transformer with a scope is a bit more complicated, and it's important to be clear about the phase relationship between the signal delivered by the current transformer and other points in the circuit. To that extent, the manufacturer has added these little arrow marks, and the idea is that when the to be measured current flows in the direction of the arrow through the core, the tip of the connector is positive. With that in mind, I have set up a source of 8 volts AC that feeds into the secondary, that is the low voltage side, of another mains transformer. That AC current is measured by the current transformer and for verification also with my red multimeter. The converted output voltage of the current transformer is connected to channel 2 of my scope. At the same time, I'm measuring the voltage across the transformer, which is connected to channel 1. The high voltage primary of that transformer is connected to a voltmeter, and there's a load resistor on it as well. That's not really necessary, but the waveform on an unloaded transformer are quite strange, and I wanted a more realistic picture. To verify the correct phase relation between channel 1 and channel 2, it is useful to imagine the AC wave frozen at the positive peak. In this case, the current flows from the source through the secondary winding, through the current transformer, in the direction of the arrow, through the multimeter and back to the source. This means the top of the secondary winding is positive, and therefore the scope's channel 1 input is also positive. For channel 2, the same is true because the current flows in the direction of the arrow on the SCT013-100. Its connector tip is positive, and because that polarity is maintained in the converter box, the output voltage for the scope's channel 2 is positive as well. So here is that setup. The mains transformer is that squarish blue box. The high voltage primary side are the yellow test leads. We see a current of about 270 milliamps on the secondary side. On the scope, we see the voltage on channel 1 in yellow and the output voltage of the current transformer in blue on channel 2. It's quite cool that although it's a voltage, of course, you can tell the scope it really is a current, and it then shows the current measurements and scale indicators. A couple of observations. First, the blue line is quite a bit fuzzier than the yellow one, which is because at 270 milliamps, even using the times 10 mode, the converted voltage is so tiny we get a lot of noise. We can also see disturbances and spikes from the mains happening every so often. Another interesting thing is that the current lags behind the voltage, which is caused by the inductance of the mains transformer. Seeing already the volts and current waveforms on the screen, we can use a math function to get power, which is, as you know, volts times current. For that, I select the operation A times B. A source for A, I use channel 1, the voltage, which is already selected. And for source B, I select channel 2, the current. Next we need to turn it on. And there we have a dark blue line that even says watts automatically because the scope knows we are multiplying volts and current. The scale of 50 watts is a bit too optimistic. Let's change this to something that's a bit more visible. 2 watts per division sounds more like it. But now we can clearly see that the noise in the current is of course also present in the trace represented by the math result. At least we can see in principle how the power curve is related to the voltage and current signals. To round things off, here is kind of the same setup, but I replaced the transformer with a light bulb. As a pure ohmic load, this should get rid of all the phase shifts between voltage and current, and with quite a bit more current flowing, we should see a little less noise. It's exactly as expected. Voltage and current are basically in phase, although as everything is coming from mains, the waveforms are not exactly symmetrically shaped sine curves, and so it's hard to tell. Noise is also much reduced thanks to the higher current. If I switch to ×100 mode, we can see the current drop because the voltage is now 1/10 of what it was before. I have to change the channel setting from ×10 to ×100 to get the correct scaling back, and with that amplification we are getting all the noise back in. It's obviously better to stay in the ×10 mode for as long as possible to get the best resolution and lowest noise. And on that topic, finally, two graphs that may be of interest. Both show the relation between input current and the converted voltage interpreted as current for the ×10 and ×100 modes. The difference between the two is the input current range. The one on the left goes all the way to 100 amps. I don't have any safe way of producing such currents, therefore I cheated by looping the measurement wire 20 times through the core, so a 5 amp current has the same magnetic field as a 100 amp current. As expected, in ×10 mode, the TVS starts to flatten the curve noticeable from about 45 to 50 amps onwards, so for currents higher than that, the ×10 mode is no longer usable, regardless what device you use for measuring the output voltage. The right graph is for very low currents, to check how long the ×100 mode remains usable. And here the result depends obviously on the meter that is used for displaying the voltage coming from the current transformer converter box. I tried 3 different instruments here, in both ×100 and ×10 mode, and for almost all meters the curves sit right on top of each other, as you would expect. The exception is the Unity UT210E, which has a best AC voltage resolution of only 1 mV. There are many other similar meters out there, for example the Fluke 101 with the same limitation. For these meters, the ×100 mode is pretty much unusable below about 1.2 amps, but as you can see, the ×10 mode works fine even for these meters down to very low currents. With these limitations in mind, I'm quite happy adding the SCT013-100 and the little converter box permanently into my toolkit. Thanks for watching.